Hi everyone, my name is Yilin Zhao from the Experimental High School attached to Beijing Normal University, and my advisor is Yifan Su from the Massachusetts Institute of Technology. And today the topic I'm going to share is seismic cloaking for underground tunnels using metamaterials, enlightened by the acoustic cloaking theory. So first to the underground, we need to learn what are lifeline tunnels in cities. In fact, it is a very easy concept. The lifeline tunnels refer to the tunnels that carry water, gas, or electricity under the city. And during earthquakes, these pipes are often prone to damage, and the disruption of these lifelines through earthquake damage can therefore have a devastating impact, threatening life in the short term and a region's economic and social stability in the long term. Because after the earthquake, some of the wires may break and people may lose internet connection, water supplies, or electric supplies. So that's really bad after an earthquake because we simply need everything to maintain our life. And also, in the academic background, the field of lifeline earthquake engineering is relatively a new one. Its formal recognition came in the 1970s with the establishment in the United States of ASCE's Technical Council on Lifeline Earthquake Engineering. And in 1975, one of the council members said that the state-of-the-art for lifeline earthquake engineering was 10 to 20 years behind that of the buildings. And even some efforts were made, many challenges remain. First of all, let's take a look at an example of a lifeline earthquake engineering project, that is the BART system. But before we get to that, we will take a look at what are the factors affecting the earthquake vulnerability of the pipelines. The first one is the velocity of seismic waves. The faster it goes, the more damage rate it would be. So there will be more repair rate per 1,000 feet. And the materials of the tubes and the joint type of tubes also hugely affect the vulnerability of pipelines. So overall, the stronger the pipes were, the less damage is prone to. And let's go in the Bay Area Rapid Transport System, San Francisco, California, USA. In 1989, it suffered from an earthquake, but it remained well and is operated and it actually operated for 24 hours. Even after the earthquake, so it's not affected at all. So let's take a look at how it is prevented from the damage that may be caused by the earthquake. First of all, it has slabs that connect the tube together, and then it has strengthened the tube wall by means of reinforcing steel arrangement in center columns or adding more concrete in the shell. So this is a kind of traditional method we have, which is quite obvious. Mostly carried out by hardening the protection layer by all means, strengthening the concrete, using some slabs. So that is literally making the whole device stronger. But we may find a paradox that in some cases, the crust can withstand the violent shaking during an earthquake, but the filling may not withstand. So we can imagine that putting a watermelon in a bulletproof jacket and then throw it down. The bulletproof crust won't break, but the watermelon may have already exploded. So for the problem statement, we're going to take a look at why is the metamaterial able to do seismic cloaking. And the implied audience to this problem is that cities often suffer from earthquakes, and who or what needs could our research address? It can guarantee people's basic supply of water or electricity after the earthquake. The big problem is how to invent a seismic metamaterial that could prevent seismic waves from penetrating the underground tunnels. It seems to be a difficult sentence, but it's quite easy to understand. Is that we have a cover made of metamaterial, and inside the cover, there is no forces. So the pressure field inside the metamaterial isn't affected by the pressure field outside the metamaterial. So this is quite easy. And if we divide it into smaller problems, we would ask, how do other people solve the acoustic cloaking problem? And the second problem is, how do acoustic problem have in similarity with the seismic wave problem? And we may see that they are both transverse waves, so that is their similarity. So it enables us to lend some concept from the acoustic cloaking theory. And what kind of metamaterial would fit? So let's go and resolve our problems in the next following slides. So we have used the alternating layer of metamaterials. This is a metamaterial that is realizable because it has two alternating layers, layers A and layer B. For each layer, it has a specific bulk modulus and density that is realizable. so that the whole metamaterial is evenly distributed with two kinds of materials. And we will dig into the theory of acoustic cloaking, which is a conformal map-based cloaking theory. For the transformation in specific expressions in terms of the physical coordinates R. Okay, so the project of the purpose of the transformation is to transform the Cartesian coordinate to the polar coordinates. You may ask the reason why. That's because the tubes are always in a circular shape, or mostly in a circular shape. So under the circumstance of a polar coordinates, it gets easy for us to analyze. So we have done on transformation here in means of calculating the QR, Q5, and QZ. That simplifies three directions. And then we have the Jacobian matrix. Jacobian matrix is literally a transformation matrix. It has some physical meaning. So if we want to transform from Cartesian to polar coordinates, we need to use this Jacobian matrix. It's partial x divided by partial x prime, and we can calculate it from the results we have given in the previous slide. And then the density and the bulk modulus can be specified by rho prime and the transformation matrix. So we have gotten the rho and bulk modulus in this slide. And then if we take all of the things in, take all of the data in, we will get the rho r, rho phi, and rho z for the metamaterial. And how is this related with the metamaterial, with exactly the alternating layer of metamaterial? Is that it has a formula here. We know rho r, we know rho phi, and we know k, which is another Romantic symbol for bulk modulus. And we also know eta. Eta is 0.5 in this case because it means the thickness of A, of material A, divided by the thickness of material A and B altogether. So we can calculate rho A, rho B, Ka, and Kb. So here are the basic diagrams of a seismic cloaking layer. The yellow part is the absorbing part, or the ambient environment. And we have the SEC, which is the so-called metamaterial cloaking layer. And inside we have concrete walls and air. And the air can be replaced by gas, by water, and even by electricity pipes as well. So the possible simulation result is that in the ambient environment, we have a very diverse or very drastic pressure field, but inside the metamaterial, the sound pressure, or as we say, the average force divided by area is 0. So here is our result in the simulation algorithm performed by COMSOL Multiphysics. We can see that the ambient pressure field is indeed drastic, but inside the metamaterial, the sound wave, the average force is 0. And on the diagram on the right, the vertical axis is the pressure of the primary wave. So for the condition of using a 50 layers cloak, the pressure becomes 0 at the cloaking area. So it's a really good result. And we have changed our frequency as well, because obviously the seismic waves have different frequencies. And from a frequency range from 0.5 hertz to 10 hertz, it has a positive result. But at 0.5, it's not working too well. It actually enlarges the pressure, but for any hertz that's bigger than 1, it works pretty well. And its performance increases, or is becoming better as the frequency increases. How about changing the relative thickness? So we found that at this condition, the 20-layer cloaks performs best, and at low relative thickness conditions. So for our conclusion, the research has successfully designed an alternating layer of metamaterial based on conformal map-based cloaking theory that can protect underground lifeline tunnels from the damage caused by primary waves. The simulation performed in the research offers a positive result. The positive protection layer could filter 90% of the ambient pressure in average at different thickness and frequencies. Better performance of the apparatus can be achieved between 1 to 10 Hz, and the thickness ratio is ranged from 0.1 to 1. And this is my references. Thank you very much for listening.